Hi, my name is Zachary Zhu, and today I will be explaining the tennis racket theorem, also known as the Zhenepikov effect. It's named after Zhenepikov because Vladimir Zhenepikov, a Russian cosmonaut, discovered it while in space in 1985. Did you notice that when I flipped my phone around this specific axis, it rotated fairly regularly? It only rotated around a single axis. So when we rotated it around this axis, it did the same thing. It stayed true to a single axis. Did you see that when I rotated my phone around this axis, the phone did a bunch of weird flips and turns? Now why is that? The reason behind this is the tennis racket theorem. The reason for the effect that we just observed is the differences in inertia along the different axes of rotation. So what is inertia? Inertia is simply an object's tendency to resist acceleration. The larger the mass, the larger the inertia. In this picture, we see that there are 4 different golf balls. If dropped, we know that all 4 golf balls will fall at the same time, but the larger ball will require more force to attain the same acceleration, because it has greater inertia. To explain the tennis racket theorem, we need to understand moment of inertia. Moment of inertia, also known as angular mass or rotational inertia, is simply an object's resistance to angular acceleration. Assuming 2 objects have the same mass, the object with more mass further from its center, in this picture, the green object, has a greater moment of inertia. This property explains why figure skaters try to keep their arms close to their body. This helps them increase angular velocity. To understand this tennis racket theorem, let's use the help of our friend Euler's equations. Here we can see Euler's equations where I1 equals the moment of inertia, omega dot equals the time derivative, you don't need to worry about that for now, omega equals the angular velocity, and m equals torque. Now let's define I1 as the moment of inertia along the first axis, I2 as the moment of inertia along the second axis, and I3 as the moment of inertia along the third axis. Now let's assume that there are torque-free conditions. Then we can see that our equations take a new form where m, or torque, is no longer present. Let's see what we can do with Euler's equations. So we'll make the assumption that I1 is greater than I2 is greater than I3. Because we assume that we are in torque-free conditions, the change in momentum along the I2 axis during a spin around axis 1 or axis 3 is proportional to I2 minus I1 times I1 minus I3. The complete derivation for this is long and tedious, so I won't go over it. But the crucial takeaway is that the change in angular momentum is negative. When I2 is not an axis of rotation, its negative momentum will dampen angular acceleration. But when an object is rotated around the I2 axis, there will be a positive rotation around the other 2 axes, so the object will be unstable. This makes axis 2 special. That's why we see the extra twists and turns as I spun my phone around in a certain orientation. Is your mind blown? Because I know Neil's is. Thank you for watching my video, and I hope that you learned something.